A telescope revealed something impossible. We thought the universe was 14 billion light-years wide, yet its true size extends up to 93 billion light-years. The James Webb Space Telescope focused on a region of the sky that no one looked at because it appeared empty and discovered 800,000 galaxies hidden in the darkness. Galaxies that formed when the universe was only 300 million years old. Black holes billions of times more massive than they should be. Structures stretching tens of millions of light-years with no time for them to have formed. Everything we believed about the size of the universe was an illusion. If you liked and subscribed, come, let's see together what is really out there.
The light coming from this galaxy set out only 280 million years after the Big Bang. It traveled through expanding space for more than 13 billion years, and finally James Webb captured it. The galaxy's name is MOMS Z14. Astronomers clearly confirmed this distance in 2025. This single discovery opened a perspective into a time when the universe had just begun to take shape, raw and unimaginably young. Here is what makes this finding striking. The universe today is 13.8 billion years old. MOMS Z14 already existed when only 2% of that time had passed. Think of it as a ratio. If the entire history of the universe were 1 year, this galaxy would have formed on January 7th. We are looking at a cosmic infancy. This discovery is the result of James Webb operating in a completely different way from previous telescopes. The telescope detects infrared radiation. Capturing this radiation, which is invisible to the human eye, created a revolution in exploring the early universe. As light travels for billions of light-years, space itself also expands. This expansion stretches the light waves, shifting them from the visible spectrum into the infrared. The farther it is, the greater the shift becomes. MOMS Z14's redshift value is 14.44. This number points to an enormous distance and surpasses the previous record by only a small difference of 10 million years. In the early universe, this span of time corresponded to an era when everything was changing rapidly.
What truly surprised scientists is that MOMS Z14 is not a small and faint point. The galaxy is bright and right in the middle of an intense star formation process. The nitrogen levels within it resemble the old star clusters we see today in the Milky Way. This indicates that the mechanisms of star formation were operating in the same way back then as well. According to old models, galaxies were supposed to grow slowly and gradually over hundreds of millions of years. MOMS Z14 proves the opposite. In April 2025, the telescope focused on this galaxy again and collected spectroscopic data. The result is clear and indisputable. This is not a theory, not a prediction, but real data belonging to a galaxy that exists at the edge of the observable universe.
What is unsettling is this. MOMS Z14 is probably not the furthest edge of this boundary. The Nancy Grace Roman Space Telescope, planned to be launched in 2027, will survey much wider areas of the sky and will most likely bring even older galaxies to light. Each new discovery pushes the boundary a little closer to the Big Bang, and each time we encounter something that should not be there, structures that formed too quickly, too bright, existing too early. The universe had 300 million years to create MOMS Z14. That time may seem long, but on a cosmic scale, it is as short as a blink of an eye. For comparison, the Earth has existed for 4.5 billion years, and dinosaurs lived on Earth for 165 million years. This galaxy assembled itself in a shorter time than the dinosaurs. Stars formed, gases collapsed, structures emerged. All of it happened in the darkness of the baby universe. What we know about galaxy formation is unraveling, and this is only the beginning.
James Webb does not see the way you do. It cannot detect visible light. Instead, it captures infrared radiation that is inaccessible to the human eye. This design choice is precisely what makes the telescope so powerful in studying the early universe. Without it, none of these discoveries would have been possible. When you look at a star, you're actually seeing light that set out from that star years ago. Even the closest star to us is 4 light years away. The light you see in the night sky left there 4 years ago. Whenever you look up, you are always looking into the past. James Webb pushes this principle to the extreme. It can capture light that has been traveling for more than 13 billion years. This telescope is also a time machine. Its infrared vision capacity is vital because of the expansion of the universe. Space expands every second. This expansion stretches everything within it, including light waves. Light that's set out as ultraviolet or visible light shifts toward longer wavelengths and turns into infrared. Objects in the early universe become almost invisible to telescopes that detect only visible light. The Hubble Space Telescope could not find galaxies like Mom's Z14 because their light was shifting beyond the spectrum that Hubble could detect.
James Webb is located approximately 1.5 million kilometers from Earth at a position called the L2 point. This point keeps the telescope permanently in the shadow of both Earth and the Sun. This is a critical requirement because the infrared sensors must be kept incredibly cold. If they heat up, they emit their own infrared glow and suppress the faint signals coming from distant galaxies. Webb's instruments operate at approximately minus 220 degrees Celsius. This is colder than the surface of Pluto. The telescope's primary mirror is 6.5 meters wide and consists of 18 hexagonal segments coated in gold. Gold reflects infrared light better than any other material. Each segment can be adjusted independently with small motors, allowing the entire mirror to achieve perfect focus. This precision enables Webb to capture objects 100 times fainter than what Hubble could see. The telescope finds early galaxies in the following way. Astronomers point Webb at specific regions of the sky for hours or even days. The longer the telescope looks, the more faint light it collects. Photons that left galaxies billions of years ago arrive one by one, and Webb's detectors count them. Over time, an image forms. Galaxies that are invisible in short observations appear in long, patient exposures. The spectrograph instruments then separate the light into individual wavelengths and create what scientists call a spectrum. Each element leaves a unique fingerprint by emitting light at its own specific wavelengths. Hydrogen looks different from helium, oxygen different from carbon. By reading these fingerprints, Webb can determine what the galaxy is made of, how fast it is moving, and most importantly, how far away it is. The redshift measurement is obtained from these spectra. It is the very key that unlocks cosmic distances. The dizziness caused by all of this lies in the following reality. Every deep field image taken by Webb reveals thousands of galaxies, and each of them is a world, a place we can never visit, where we see the universe in its childhood.
Close your eyes and imagine absolute darkness. The first few 100 million years of the universe looked exactly like this. There were no stars anywhere, no galaxies, only hydrogen and helium gas slowly gathering together under the pull of gravity, drifting through space. This period, called the Cosmic Dark Ages, lasted far longer than you might think. Then something changed. Gravity won. Gas collapsed into dense pockets, pressure increased, temperatures rose, and the first stars ignited. That moment ended the Dark Ages and ushered in the cosmic dawn. MOMS Z14 formed during this dawn, the era when the universe first began to fill with light. Although 280 million years seems like a long time, it is not enough to build a galaxy. Gas must collapse, stars must form, these stars must cluster, heavy elements must be synthesized inside stars, and multiple generations of stars must complete this cycle. Each step takes time, yet MOMS Z14 completed all of this in under 300 million years. Back then, the universe was much smaller, everything was closer, matter was more densely packed, and the average temperature was higher. Radiation left over from the Big Bang still filled the cosmos, but it had cooled significantly. Rings of dark matter began to form, creating gravitational wells where normal matter could gather. These rings served as an invisible skeleton for the first galaxies. The gas itself was almost entirely hydrogen and helium. Oxygen, carbon, nitrogen, and the elements that form planets or life did not yet exist. All of these had to be synthesized inside stars first. When massive stars exploded as supernovae, they scattered heavy elements into space. The next generation of stars incorporated these elements. This process, called stellar nucleosynthesis, requires multiple cycles and explosions, meaning it takes time.
What surprises scientists is this. MOMS Z14 already carries traces of nitrogen. This means that at least 1 or 2 generations of stars were born and died within the galaxy. In less than 300 million years, stars formed, burned through their fuel, exploded, enriching the surrounding gas, and new stars formed from this enriched material. The time frame is almost impossibly compressed. To compare this with our own galaxy, the Milky Way has existed for more than 13 billion years and has gone through countless cycles of star birth and death. The iron, silicon, gold, and uranium contained on Earth, all of these elements did not exist when the universe was young and come from ancient supernovae. MOMS Z14 initiated the same process in a much shorter period. And it is not alone. James Webb has detected over 100 galaxies from this early era. Each one is bright, each in the midst of active star formation, and each challenges models that predicted galaxies should develop slowly. The cosmic dawn was not gradual, it happened in bursts. Galaxies appeared rapidly, shone intensely, and transformed the universe from darkness to light in just a few 100 million years. We can see the evidence for this only now, 13 billion years later, because it took that long for the light to reach us. In a galaxy called Canex LRD Z86, there is a black hole. The galaxy existed only 570 million years after the Big Bang. That alone is impressive, but what makes it impossible is the size of the black hole, millions of times heavier than our Sun, a colossal object consuming matter at a rate exceeding theoretical limits. Black holes form when massive stars collapse. When a star 20 times heavier than our Sun explodes as a supernova, its core may become a black hole about 50 times the mass of the Sun. These are stellar mass black holes, small compared to supermassive black holes. But how do you go from 50 to millions? You need time, a lot of time. The black hole must consume gas, dust, and other stars over hundreds of millions or even billions of years. Here lies the problem. Canex LRD Z86 did not have that much time. The universe was only 500 million years old when this galaxy existed. That period is far too short for a supermassive black hole to reach such mass through normal growth. Yet there it is, confirmed by James Webb spectroscopy. Not a theory, not speculation, real data. This galaxy belongs to a class called little red dots. These objects are small, faint, and extremely red due to their distance. Since James Webb began operations, it has discovered dozens of them. Most surprise astronomers. Either their star densities are too high for their size, or the black holes they contain are disproportionately large compared to the host galaxy. Canac's Lard Z86 falls into the second category. The black hole's mass significantly exceeds the total mass of stars in the galaxy. How did it reach such a size so quickly? There are two main theories. According to the first, the black hole originates from a massive gas cloud that collapsed directly before any star formation. This produces an object thousands of solar masses in size from the start, called a heavy seed black hole, giving it a serious head start. In the second theory, supermassive stars come into play. These hypothetical objects, never yet observed, would be hundreds or thousands of times heavier than normal stars, and when they collapse, they would instantly leave behind large black holes. Both theories have problems. Direct collapse requires very specific conditions, while supermassive stars remain theoretical. Yet, something created these black holes, because we can see them now.
The accretion rate makes the situation even more complicated. James Webb detected gas orbiting the black hole at incredible speeds. The gas is highly ionized, meaning radiation from the black hole strips electrons from atoms. This is a signature of rapid accretion. The black hole is consuming matter at over 40 times the theoretical Eddington limit. This limit is the theoretical maximum rate at which a black hole can feed before its radiation pressure pushes incoming matter away. Imagine there is a speed limit set by physics, and this black hole exceeds it 40-fold. It's like saying a car with a speed limit of 160 kilometers per hour somehow traveled at 6,400 kilometers per hour. Physics should not allow this. If this object continues to feed, it will become a monster in a relatively short time. What truly worries scientists is this. If Canac's LRD Z86 is not unique, and there are thousands or millions of such galaxies in the early universe, supermassive black holes formed much faster and much more easily than we thought. They did not need billions of years to grow. They appeared early, hungry, and ready to consume everything around them. The young universe was wild, violent, and as James Webb continues to look into the past, every rule we thought governed black hole growth is being rewritten. James Webb started finding them immediately. Tiny red specks scattered across deep field images. Astronomers initially thought they were ordinary distant galaxies. Then the spectroscopy results arrived. These objects are not normal, not even close. Compact, extremely bright, and their properties make no sense. Standard models agree. Scientists call them little red dots, and they are rewriting all the rules of early galaxy evolution. More than 100 have been detected so far, and they all share common features. Much smaller than typical galaxies of the same era. Red because cosmic expansion shifts their light. Disproportionately bright for their size. And finally, they contain either dense star clusters that should not exist or massive black holes that should not fit inside them.
Here's what makes them strange. When you calculate the stellar mass required to produce their brightness, you encounter an impossibly high density. The stars would be so crowded that they would constantly collide and merge. Nothing like this occurs in any galaxy we see today. Alternatively, if a supermassive black hole produces the light, it must be far too large for the host galaxy. In modern galaxies, black holes carry roughly 1/1000th of the galaxy's total mass. In little red dots, the black hole rivals the combined mass of all the stars in the galaxy. Both scenarios break the models. Astronomers thought galaxies and their central black holes grew together in a balanced ratio. The galaxy forms first, gradually accumulating stars. The black hole grows more slowly, swallowing gas falling into the center, eventually reaching equilibrium. Little red dots show this relationship reversed.
The black hole grew first, leaving the surrounding galaxy behind. Another mystery lies in their abundance. Before James Webb, astronomers expected to find perhaps a handful of unusual galaxies in the early universe. Instead, they encountered hundreds. Not rare coincidences, widespread objects. This shows that the process that created them was not an exception, but a standard part of early universe behavior. Some scientists think little red dots are transitional objects, galaxies caught in the middle of a growth burst, where the central black hole rapidly grows while the surrounding galaxy has not yet caught up. Over time, the galaxy could gain more stars and evolve into a bright, active galactic nucleus. If true, little red dots are snapshots of a youthful phase all galaxies pass through before maturing. Others argue they represent a completely different formation pathway. Perhaps some galaxies form black holes first and then develop stars around them. Perhaps dark matter plays a far larger role than we imagined. Perhaps the early universe allowed black holes to grow much faster under conditions no longer present today. One thing is certain, little red dots are not going away. Every new James Webb observation reveals more, showing they existed everywhere in multiple phases throughout the universe's first billion years. The most unsettling part is what they tell us about our models. We developed equations to describe how galaxies form, ran simulations. These simulations predicted slow, steady growth, star formation over billions of years, black holes remaining small relative to their host galaxies. Little red dots discard all three predictions. The young universe was not patient, it was chaotic, fast, and dense. Little red dots are proof of this, scattered across the sky, cosmic mysteries waiting to be unraveled.
Physics has limits. The rules governing how fast black holes can consume matter are not mere suggestions, they are direct consequences of radiation pressure and gravitational forces. Yet, the black hole called LID 568 completely ignores these rules, and astronomers have no explanation for it. Located at the center of a dwarf galaxy, this object is observed as it existed 1.5 billion years after the Big Bang. James Webb and the Chandra X-ray Observatory examined it together. The data is clear. LID 568 is feeding at more than 40 times the Eddington limit. How does this limit work? As matter falls toward a black hole, it forms a disk orbiting around the event horizon. Friction in this disk heats the matter to millions of degrees. The heated matter emits radiation, including intense X-rays. This radiation exerts outward pressure. If too much matter falls too quickly, the radiation pressure becomes strong enough to push incoming matter away. The black hole effectively chokes itself. This creates a natural speed limit. LID 568 exceeds this limit 40-fold. 40 times, not 10%, not twice, but exactly 40 times. Physics should not allow this.
One possibility is super Eddington accretion. This occurs when matter falls in simultaneously from all directions, overwhelming radiation pressure with sheer volume. If enough gas collapses into the black hole at once, the radiation cannot push it all back quickly enough, and the black hole experiences a short, intense feeding frenzy. Such feeding frenzies are likely rare and short-lived. Once the surrounding gas supply runs out, the black hole cannot feed at this rate for millions of years. What makes LID 568 remarkable is that astronomers have caught it in this brief phase. This is a snapshot of the kind of event that could explain how supermassive black holes grew so quickly in the early universe. The black hole's mass is relatively small on the supermassive scale, only a few million solar masses. Given how young the universe was when LID 568 formed, this makes sense. What is puzzling is how luminous it is. The energy radiated from the accretion disk is enormous. X-rays are thrown into space, heating the surrounding gas until it glows. If this feeding rate lasted only a few million years, the black hole would have doubled its mass. Scientists think such events may have been common in the early universe. Gas was denser, galaxies were still forming, structures chaotic and unstable. Massive gas clouds could collapse onto young black holes, triggering super Eddington feeding bursts. Each burst adds significant mass. With multiple bursts, it could be possible to grow from a stellar mass black hole to a supermassive one in far less time than normal accretion would require. James Webb's discovery of LID 568 provides critical evidence for this theory. Before, super Eddington accretion was hypothetical. Now we have observed it and measured it. We know it happens. The question is no longer whether it's possible, but how frequently it occurred. The universe is far stranger than equations suggest. Black holes do not always obey the limits we calculate. Under the right conditions, they break the rules. In the early universe, those right conditions may have been everywhere.
For a moment, extend your arm and imagine holding a grain of sand against the sky. Behind the area that grain covers, there are roughly 800,000 galaxies. The Cosmos Webb survey revealed this after James Webb focused on a single patch of sky for over 200 hours. The survey covers 0.6 square degrees of the sky. By comparison, the full moon covers about 0.2 square degrees, so this area is roughly 3 times the size of the full moon. On a cosmic scale, this is a microscopic slice, but within it lie more galaxies than most humans can grasp. 800,000 galaxies, each containing billions or trillions of stars, each at a different distance, corresponding to a different moment in the history of the universe. The nearby ones show galaxies from relatively recent times. The light from the farthest began its journey over 13 billion years ago. The survey makes all these times visible in a single image, creating a timeline of cosmic history. The Cosmos Webb project used James Webb's near-infrared camera and mid-infrared instruments to collect data. Astronomers specifically chose the Cosmos field because foreground stars or gas clouds that could block the view are extremely sparse, providing a clear line of sight into the depths of space. This field had been studied over the years by many telescopes, including Hubble, but Webb's infrared sensitivity revealed galaxies that Hubble completely missed. What makes this survey groundbreaking is that it combines width and depth. Many deep field images maximize observation time to see the faintest objects, focusing on very tiny areas. Cosmos Webb sacrificed some depth to scan a wider area, revealing how galaxies are distributed in space. The result is a map showing galactic structures, clusters, and voids spanning billions of light years. The image contains galaxies at every stage of evolution: spiral galaxies with elegant arms, smooth and featureless ellipticals, irregulars twisted by gravitational interactions, merging systems, and scattered little red dots, remnants of the cosmic dawn.
An unexpected finding is just how numerous early galaxies are. Before James Webb, models predicted far fewer bright galaxies in the first billion years after the Big Bang. The Cosmos Webb survey found 10 times more than expected. This shows that galaxy formation occurred faster and more efficiently than theories had predicted. The early universe was not empty and calm, it was crowded and dynamic. The survey also revealed that structures formed earlier than anticipated. Groups and clusters of galaxies that should have taken longer to assemble were already visible in the early universe. Gravity gathered galaxies faster than models suggested. The cosmic web, the large-scale structure of the universe with filaments and voids, had already begun forming when the universe was only a few billion years old. Every galaxy in the image has a story, each formed through a unique combination of dark matter, gas collapse and star formation. Some underwent violent mergers, others grew quietly over billions of years. Some are actively producing stars. Their light carries the brightness of young, hot stellar populations. Others are old and dead. Their stars have long burned out, leaving only the ghostly echo of past activity. The Cosmos Web Survey will be studied for years. Astronomers will analyze individual galaxies, measure their distances, examine their compositions, and track how they change over time. Every new analysis sharpens our understanding of the cosmic universe. Every discovery adds another piece to the puzzle of how the universe grew from the fireball of the Big Bang to the structured cosmos we see today. And this is just one patch of sky. There are more than 40,000 square degrees across the entire celestial sphere. If each patch contains this many galaxies, the total number in the observable universe exceeds 2 trillion. This number is so vast that it loses meaning. It exists only as a symbol of the universe's incomprehensible scale.
A black hole is moving through space at an astonishing 3.2 million kilometers per hour. It isn't orbiting anything. It isn't falling toward anything. It's fleeing, escaping into the cosmos, leaving behind a 200,000 light-year-long tail of newborn stars, like a cosmic scar. The black hole is 10 million times more massive than our Sun, supermassive by any measure. Yet something has ejected it from its home, a force propelling it at 3,000 times the speed of sound. James Webb confirmed this discovery in 2025, and astronomers are calling it the first verified runaway supermassive black hole. The object resides in the Cosmic Owl galaxy system, which is actually multiple galaxies in the process of merging. When galaxies collide, the central black holes normally sink toward the core of the merged galaxy. In rare cases, gravitational interactions can completely eject one of the black holes. That is exactly what happened here. There are two ways to accelerate such a massive black hole. The first is during the merger of two supermassive black holes, which emits gravitational waves. These waves carry momentum, and if emitted asymmetrically, they can recoil the merged black hole at high speed, enough to escape the galaxy's gravity, like a cosmic gunshot. The second involves three black holes. If a galaxy's center already hosts a binary pair and a third black hole enters during a merger, the interaction becomes unstable. This is the classic three-body problem, a chaotic gravitational dance with no stable solution, where one member is inevitably ejected. James Webb detected a shock wave in front of the black hole as it moved. The black hole plows through intergalactic gas at incredible speed, compressing the gas ahead of it and creating a shock wave similar to the bow wave of a boat. The compressed gas heats up and glows. The telescope also detected the trail behind the black hole, a filament where gas collapsed and formed stars. Its passage triggered star formation along its entire path. This is unprecedented, stars forming in the wake of a runaway black hole. Gravity compresses the gas, causing it to collapse, and new stars ignite in the wake of the fleeing giant. The trail is visible because the young stars are bright, emitting ultraviolet and visible light that shifts to infrared by the time it reaches us.
The speed is mind-blowing. 3.2 million kilometers per hour. In a single second, the black hole travels more than 500 meters, covering the distance from Earth to the Moon in under 2 minutes. At this velocity, it will soon leave the Cosmic Owl system entirely, roaming intergalactic space as a rogue object. Galaxies without central black holes are rare. This galaxy will soon be homeless. What does this discovery mean for our understanding of black hole evolution? Runaway black holes had been predicted in simulations, but spotting one proves they exist. It also raises questions about their prevalence. If galaxy mergers frequently eject black holes, there may be thousands of rogue objects drifting in space, invisible because they are no longer accreting matter. The finding also suggests that black hole mergers in the early universe were chaotic. During the cosmic dawn, as galaxies formed and collided, black holes experienced violent interactions. Some merged, some were ejected. The process was messy, unpredictable, and left the cosmos scattered with wandering black holes. James Webb's detection demonstrates how sensitive the telescope is to faint structures. The shockwave and star trail are not bright. They require long exposures and careful analysis. Yet it revealed something no one had seen before: a supermassive black hole fleeing its home, leaving a trail of creation in its wake. In the ZS7 galaxy system, two black holes are colliding. This system existed just 740 million years after the Big Bang. Both are supermassive, each millions of times the mass of the Sun. They orbit each other, spiraling inward, and will eventually merge into a single larger black hole. When that moment comes, the collision will ripple through space-time. James Webb detected the merger by analyzing the light spectrum of ZS7. The data revealed two extremely energetic radiation sources in close proximity. Both sources exhibit the signatures of accreting black holes: fast-moving gas, highly ionized material, and broad emission lines from atoms spinning at incredible speeds. The two sources are only a few thousand light-years apart and moving toward each other.
This is the most distant black hole merger ever detected, and also the earliest in cosmic time. Previous mergers have been observed in the modern universe, but none reached so far back. This discovery confirms that black holes collided and merged before the universe was even a billion years old. This has major implications for the rapid growth of supermassive black holes. Mergers are one of the fastest ways to build massive black holes. Instead of slowly accreting gas over millions of years, two black holes can combine their masses in a single event. If mergers were common in the early universe, it could explain how supermassive black holes reached billions of solar masses within the first billion years after the Big Bang. The merger process itself is fascinating. As the two black holes orbit each other, they emit gravitational waves, ripples in space-time predicted by Einstein's general relativity. These waves carry energy away from the system, causing the orbits to shrink. The black holes spiral closer, accelerate, and eventually collide. The final merger occurs in a fraction of a second, releasing more energy than all the stars in the observable universe combined. The gravitational waves from ZS7 are too faint to detect with current technology. After traveling 13 billion light-years, they've weakened considerably. However, future observatories will be able to capture them. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, is designed specifically to detect gravitational waves from supermassive black hole mergers. When operational, it will routinely observe events like ZS7. This discovery is critical because it offers a preview of what LISA will encounter. Before James Webb found mergers in the early universe, scientists assumed events like ZS7 were rare. Now they know mergers were common, meaning the baby universe experienced a far higher rate of black hole mergers than models predicted.
Mergers also teach us about galaxy evolution. ZS7 formed from the collision of two galaxies. During this process, each galaxy's black hole moves toward the center of the newly merged galaxy. This happens through a process called dynamical friction, in which black holes lose energy by interacting with stars and gas, spiraling inward. Eventually, they form a binary pair, which ultimately merges. This sequence has occurred repeatedly throughout cosmic history. The Milky Way is currently on a collision course with the Andromeda Galaxy and will merge with it in about 4 billion years. When that happens, the central black holes will eventually merge too. What we see in ZS7 is exactly what our own galaxy will experience in the distant future. The gravitational waves from ZS7's merger originated 13 billion years ago and have been traveling through space ever since. As the universe expands, these waves stretch into long wavelength signals detectable only by space-based observatories like LISA. They carry information about the black hole's masses, spins, and the dynamics of the merger. Future astronomers will decode this data, revealing details that James Webb cannot directly observe. There is also a galaxy called Jade's GS Z14-0. It existed just 290 million years after the Big Bang. James Webb measured its brightness and made a striking discovery. The galaxy forms stars 100 times faster than models predicted for its age. Star formation requires gas. Hydrogen clouds collapse under gravity, compress, and heat up. When temperatures reach around 10 million degrees, nuclear fusion ignites, hydrogen atoms turn into helium, and energy is released, birthing a star. The process takes millions of years from start to finish and requires specific conditions. The gas must be dense enough, cool enough, and turbulence cannot disrupt the collapse. In the modern universe, galaxies produce stars relatively slowly. The Milky Way forms about 3 new stars per year. While this may seem fast, our galaxy contains hundreds of billions of existing stars. Compared to total stellar mass, the star formation rate is low. For mature galaxies, most of the gas inventory has already turned into stars or been ejected via supernova winds. This is typical for galaxies in the modern era.
Jade's GS Z14-0 is different. It forms stars at a rate equivalent to hundreds or even thousands of solar masses per year. For a galaxy of this age and size, this rate is extreme. Gas clouds across the galaxy are collapsing simultaneously. The entire volume has become a stellar factory. Why is this happening? One theory involves cold gas streams flowing into the galaxy from its surroundings. In the early universe, gas was distributed differently than today. Dark matter halos pulled gas across vast distances, which flowed along filaments like rivers feeding young galaxies. This constant inflow provided an uninterrupted supply of raw material for star formation. Another possibility is a recent merger. When 2 galaxies collide, their gas clouds crash together, triggering massive bursts of star formation. Collisions compress gas, causing widespread collapse. Star formation rates can spike tenfold or more during such events. Jade's GS Z14-0 may have been caught in the midst of such a burst. Its brightness is also a puzzle. Young stars are hot and luminous, emitting enormous amounts of ultraviolet light that heats surrounding gas and causes it to glow. Even accounting for the star formation rate, the galaxy is brighter than expected. This suggests either unusually massive stars or an additional energy source contributing to the luminosity. Some astronomers speculate supermassive stars might be involved, hypothetical objects hundreds of times more massive and hotter than normal stars, living only a few million years before exploding. If Jade's GS Z14-0 formed such a population, their combined light could explain the extreme brightness. However, supermassive stars remain theoretical. No confirmed observations exist.
The galaxy's spectrum shows strong emission lines from oxygen and hydrogen, confirming active star formation. The lines are broader than expected, indicating turbulent gas moving at high speeds. This turbulence can partly be explained by stellar winds and supernova explosions. Young, massive stars die rapidly and violently, injecting energy into their surroundings.
This energy stirs the gas, creating chaotic motion. What troubles scientists is the short time scale. Just 290 million years after the Big Bang, the universe should have barely begun forming its first generation of stars. It should not have had time to establish a large-scale stellar factory. Yet JADES/GS/Z14/0 is fully operational, forming stars at an unprecedented rate. This suggests that galaxy formation in the early universe was far more efficient than current models predict. Gas collapsed faster, stars formed more quickly. Feedback mechanisms that slow star formation in modern galaxies were weaker or absent.
The early universe provided a much more efficient environment for building galaxies. Every new discovery, like JADES GS-Z14-0, forces astronomers to revise their models. Numbers are updated, timescales compressed, and the picture of the early universe becomes increasingly chaotic, violent, and awe-inspiring. We've known since the 1920s that the universe is expanding. What we do not know precisely is how fast it is expanding. Two different measurement methods give different answers, and this discrepancy is too large to ignore. Astronomers call this the Hubble tension. James Webb has just confirmed it is real. The expansion rate is expressed by a number called the Hubble constant. This constant indicates how fast galaxies at a given distance are moving away from us. For example, if the Hubble constant is 70, a galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 2 megaparsecs away moves at 140 kilometers per second. As distance increases, the recession speed increases proportionally.
There are two main ways to measure this constant. The first method uses the cosmic microwave background, or CMB, the afterglow of the Big Bang. This radiation fills the entire universe and carries information about the universe just 380,000 years after the Big Bang. Scientists analyze tiny temperature variations in this radiation to calculate the expansion rate at that time, then project it to today using cosmological models. This method gives a value of roughly 67. The second method relies on nearby stars and galaxies. Astronomers use Cepheid variable stars and Type 1a supernovae as distance markers. By comparing the distances and recession speeds of these galaxies, they can calculate the Hubble constant directly. This method gives a value of about 73. A 6-point difference may seem small, but it is significant. It is not a rounding error or measurement uncertainty. Both methods are precise and have been repeatedly verified. The discrepancy is real and has persisted for over a decade. This is the so-called Hubble tension.
James Webb's role in this mystery is critical. The main concern was that Hubble's Space Telescope measurements might have been flawed. Perhaps distances were wrong, or Hubble's observations of Cepheid stars introduced a systematic bias. James Webb can observe the same stars with higher sensitivity and resolution. If Hubble's measurements were wrong, Webb would have found a different value. It did not. Webb confirmed Hubble's results. The distances are correct. When measured with nearby objects, the expansion rate is indeed about 73. The tension is not caused by observational error, it is real. This leaves two possibilities. Either our cosmological model is incomplete, or the expansion of the universe changes over time. The standard model of cosmology assumes that the expansion rate follows a predictable pattern determined by the amounts of matter, and dark energy. If these assumptions are wrong, the model breaks down. One idea is that dark energy behaves differently than assumed. This mysterious force driving the universe's acceleration constitutes roughly 68% of the total energy of the universe. We don't know what it is, only that it exists. If the strength of dark energy changed over cosmic history, it could explain the tension. The early universe might have expanded at one rate, while today it expands at another.
Another possibility is the existence of an unknown component we haven't discovered yet, some new form of energy or matter affecting expansion. Finding this would be equivalent to discovering a missing ingredient in the recipe of the cosmos. Alternatively, the problem could lie in the models used to interpret the cosmic microwave background. If the early universe was different from what we assumed, projections to today would be wrong. The Hubble tension remains one of modern cosmology's biggest mysteries, signaling that our understanding of the universe is incomplete. At the foundation of our cosmic models, there is a crack. In another discovery, James Webb observed a galaxy named LAP-1b as part of a search for unusual objects in the early universe. Its spectrum was strange: no oxygen, no carbon, almost only hydrogen and helium. This could be the signature of population 3 stars, the very first stars ever formed. Stars are categorized by metal content, where metal in astronomy means any element heavier than helium, including iron, carbon, and oxygen. Modern stars, called population 1, have a few percent of their mass in metals. Older stars, population 2, contain far fewer metals, roughly 1 part per thousand. Population 3 stars formed just after the Big Bang from pure hydrogen and helium with 0 metals. No one has ever definitively observed a population 3 star. They must have existed, but they died billions of years ago. These stars were extremely massive, consuming their fuel in just a few million years before exploding as supernovae. These explosions seeded the first heavy elements into space, providing the raw material for the next generation of stars. Our Sun and all stars we see today carry the metals forged by population 3 stars.
They are difficult to find because they are extremely ancient. A still shining population 3 star could only exist in the most distant galaxies and would reach us only as it appeared in the early universe. Their light would be faint and redshifted. Even James Webb struggles to detect individual stars at such distances. So instead, astronomers search for galaxies where population 3 stars might still dominate the stellar population. LAP-1b is a candidate. The galaxy's spectrum shows almost no metal lines. The light is dominated by hydrogen and helium emission. This could indicate that the galaxy consists mostly of population 3 stars. However, other explanations are possible. The galaxy may contain extremely pristine gas not yet enriched by supernovae, or the spectrum could originate from gas clouds rather than stars. Confirming population 3 stars requires deeper observations. James Webb must observe longer, collect more photons, and detect fainter spectral features. A complete absence of oxygen would strengthen the case. Population 3 stars explode before producing it, while oxygen is created in the nuclear fusion and explosions of later generations. Why does this matter? Population 3 stars shaped the universe. After the cosmic dark ages, they were the first sources of light. Their ultraviolet radiation ionized the surrounding hydrogen gas, transforming neutral gas into plasma. This process is called reionization and fundamentally altered the structure of the universe. Without them, reionization would not have occurred, and the universe would look entirely different today. These stars also laid the groundwork for all future star formation. By creating the first heavy elements, they made planets possible: carbon, oxygen, silicon, iron. All the matter that forms Earth comes from supernovae of massive stars. Population 3 stars initiated this process. They were cosmic alchemists, transforming simple hydrogen and helium into the complex periodic table we rely on today.
Their masses remain debated. Some models suggest they were hundreds of times more massive than our Sun. Others propose a range between 10 and 100 solar masses. The difference matters because it affects how they exploded and which elements they produced. Extremely massive stars may have collapsed directly into black holes without exploding. If so, they would not have enriched the universe with metals, potentially delaying the formation of later generations of stars. James Webb's discovery of LAP-1b offers a rare opportunity to glimpse what the first stars looked like. Even if this galaxy does not ultimately contain population 3 stars, it proves that Webb has the capacity to detect such pristine objects. As the telescope continues surveying the early universe, astronomers will eventually find definitive evidence of these ancient giants. When that day comes, the full story of stellar evolution will be complete. From the first generation to our own, we will have observed stars from every era and understand how they transformed the universe from a simple hydrogen-helium cloud into the rich, complex cosmos we inhabit today. James Webb continues to find massive galaxies within the first billion years after the Big Bang. These are not small dwarf galaxies just beginning to form their first stars. They are large, mature systems containing billions of stars. They should not yet exist. The universe did not have enough time to build them. Galaxy formation is supposed to be gradual. First, dark matter halos form, creating gravitational wells. Gas falls into them, accumulating over tens or hundreds of millions of years. Eventually, enough gas gathers and star formation begins. The galaxy grows slowly, increasing its mass through continuous star formation and mergers with smaller galaxies. Reaching tens of billions of solar masses should take at least 1 billion years, yet James Webb has found galaxies of exactly this mass at redshifts of 9, 10, even 11, a time when the universe was less than 500 million years old. Some date back to just 300 million years after the Big Bang, and their mere existence is enough to shake the timeline.
For example, consider a galaxy with a redshift of 11. Data show it contains the equivalent of 10 billion solar masses in stars and gas. This is not a small galaxy. In terms of mass, it is comparable to the Large Magellanic Cloud among the Milky Way's satellite galaxies. The problem is its age. At redshift 11, the universe was only 400 million years old. Building 10 billion solar masses in that time requires star formation rates far higher than models predict. These galaxies are not only massive, but also mature. Their spectra show traces of older stellar populations. The stars have been there for some time. Some even show the presence of dust. Dust forms from supernova remnants and takes time to accumulate. This indicates that the galaxy has already gone through multiple cycles of star formation and death.
How did they grow so quickly? One idea points to extremely efficient star formation. Perhaps the first galaxies converted gas into stars 10 to 20 times more efficiently than modern galaxies. If star formation was this effective, galaxies could reach large masses in a short time. However, this requires explaining why efficiency was so high. What conditions in the early universe made star formation this effective? Another possibility is that dark matter halos grew faster than in current models. Halos merged more quickly, pulled in gas faster, and accelerated galaxy growth. This could occur if dark matter had properties we haven't accounted for, or if density fluctuations in the early universe were stronger than expected. Mergers may also have played a role. Small galaxies forming early and merging quickly could gather mass in larger systems faster. Yet mergers alone cannot explain the most massive galaxies. There simply wasn't enough time for the required merger frequency. Some scientists suggest that observations may be misinterpreted. If galaxies host overly bright stars or active black holes mimicking many stars, masses could be overestimated.
Spectroscopy largely rules this out. The light from stars carries a different signature than black hole emission, and most of these galaxies are star-dominated in their spectra. The discovery of massive early galaxies forces a rethink of galaxy formation models. Equations describing structure formation in the universe may need updating. Parameters controlling star formation might need adjustment, or entirely new physics might be at play, something we hadn't considered because we had never observed the universe this early. Each massive galaxy James Webb discovers adds another piece to the puzzle. Each one pushes the limits of what seems possible, revealing a universe far more dynamic, active, and capable of rapid growth than previously imagined. Imagine holding out your hand at night and a single grain of sand blocks the sky. Behind that tiny patch, more than 10,000 galaxies lie. This is not an exaggeration. It is what James Webb revealed by focusing for 12.5 hours on the SMACS 0723 galaxy cluster to produce its first deep-field image. The image covers such a small portion of the sky that you could block it with a needle's tip. Yet within this tiny patch, the universe displays its full scale. Galaxies are compacted, overlapping, and interwoven. Some are bright spirals with clear structure, others faint smudges barely visible against the black background. A few of these galaxies' light has traveled over 13 billion years to reach us. The SMACS 0723 galaxy cluster is about 4 billion light-years away. The cluster itself is enormous, holding hundreds of galaxies together through gravity. The combined mass of these galaxies warps space-time so strongly that light from galaxies far behind is bent and magnified, making otherwise invisible faint objects visible. This effect is called gravitational lensing, predicted by Einstein's general relativity equations. Massive objects curve space-time, and light passing through this curved space follows a bent path. The result is similar to how glass lenses bend light to form an image. The galaxy cluster acts as a cosmic magnifying glass, revealing distant galaxies. Some of the galaxies in the image appear stretched into long arcs, distorted by the lensing effect. These arcs are actually single galaxies whose light is bent around the cluster before reaching us. By analyzing the distortions, astronomers can calculate the distances and masses of these galaxies. The faintest objects in the image are also the oldest. Their light began its journey when the universe was less than 1 billion years old. These galaxies appear red because cosmic expansion has stretched their light. What started as ultraviolet radiation has shifted into infrared wavelengths. James Webb's sensors are designed precisely to detect this kind of light, making the telescope ideal for finding the universe's most ancient structures. Each galaxy in the image has its own unique history. Some are young and actively forming stars. Some are old and dying, their stellar populations fading. Some have undergone mergers that distorted their shapes, while others have grown quietly for billions of years without disturbance. The diversity is astonishing. No two galaxies are alike. The deep field image also reveals the large-scale structure of the universe. Galaxies are not randomly distributed. They cluster into groups and chains, forming a cosmic web. The filaments of this web stretch hundreds of millions of light-years with vast voids in between. The SMACS 0723 cluster sits at a node of this web where multiple filaments intersect. James Webb captured this image over 12.5 hours. The Hubble Space Telescope would have required weeks to reach similar depth. This leap in efficiency allows James Webb to survey larger swaths of the sky in less time, discover more galaxies, and build a more complete picture of cosmic history. The image is just the beginning. Astronomers will spend years analyzing it, measuring the properties of individual galaxies, calculating distances, and studying how galaxy populations evolve over time. Each galaxy offers clues about processes that drive star formation, chemical enrichment, and cosmic evolution.
What makes this image so profound is the sense of scale. In that tiny patch of sky lie thousands of galaxies. The entire sky covers over 40,000 square degrees. If each patch hosts a similar density of galaxies, the total number in the observable universe reaches into the trillions. Trillions! Each potentially containing billions of planets, each a universe unto itself, filled with stars, worlds, and mysteries we may never reach. The sand grain analogy is apt, yet also literal. The vastness of the cosmos is almost incomprehensible. We can capture it in images, quantify it with numbers, but truly grasping it eludes the mind. All we can do is marvel at the images and accept how small our corner of existence truly is. Light does not travel in straight lines near massive objects. Where mass is concentrated, it curves space-time, bending the path of light. This effect, called gravitational lensing, turns galaxy clusters into natural telescopes that reveal the universe's most distant structures. Galaxy clusters contain thousands of galaxies, each contributing mass. Dark matter, 5 times more abundant than visible matter, creates an even larger gravitational field unseen.
The combined field is immense, warping space-time over millions of light years. Light from a background galaxy passing near the cluster is often deflected in multiple directions. A single background galaxy can therefore produce multiple images. The light takes different paths around the cluster to reach our telescope from different angles. Each path creates a separate image, sometimes forming arcs around the cluster, sometimes appearing as isolated fragments scattered across the sky. By analyzing the positions and shapes of these images, astronomers can reconstruct how the original galaxy appeared and calculate its distance. Gravitational lensing also magnifies light. The bending effect concentrates photons, making the background galaxy appear brighter. Sometimes magnification boosts a galaxy's apparent brightness by tenfold or more. Galaxies too faint for James Webb to detect on its own become visible thanks to this lensing. A famous example is the cosmic horseshoe, an almost perfect ring created when a distant galaxy is lensed by a foreground cluster. The ring is not a physical structure, but the stretched and wrapped image of a single galaxy around the cluster's gravitational field. Without the lens, this galaxy would remain a faint smudge. The lens transforms it into a spectacular arc across the sky.
James Webb is using the gravitational lensing effect to reach depths that would otherwise be inaccessible. By targeting galaxy clusters that create strong lensing, it can observe galaxies from the first few 100 million years after the Big Bang. These galaxies are so distant and faint that without the magnification provided by the clusters, they would be completely invisible. The challenge of lensing is that it distorts the image. The galaxy's shape stretches, bends, and fragments. Reconstructing its original appearance requires complex models that account for the cluster's mass distribution. Astronomers map the cluster's gravitational field by analyzing how it lenses multiple background galaxies. Once they understand the field, they can reverse the lensing effect and determine how the galaxies truly appear.
Another benefit of gravitational lensing is that it allows the study of dark matter. The lensing strength depends on the total mass in the sky, including the invisible. By measuring lensing, astronomers map the dark matter distribution in clusters. These maps often reveal a dense central region surrounded by diffuse halos extending far beyond the visible galaxies. Occasionally, lensing produces a rare phenomenon called an Einstein ring. When a background galaxy, the lensing object, and the observer are perfectly aligned, the galaxy's light bends equally in all directions, forming a complete ring. Einstein rings are both beautiful and scientifically valuable. The ring's radius depends on the lensing mass, allowing precise measurement of the cluster's weight. The universe's most powerful lenses are merging galaxy clusters. When two clusters collide, their combined mass creates a far stronger gravitational field, producing extreme lensing effects that can magnify background galaxies 50 times or more. James Webb has used a few merging clusters to reveal galaxies that would otherwise be impossible to see. Gravitational lensing is one of the rare tools that allow astronomers to study the oldest galaxies in the early universe in detail. Without it, objects from the cosmic dawn would remain forever invisible, too faint and distant even for the strongest telescopes. The universe has gifted us these natural magnifiers, and James Webb uses them to peer into depths never explored before.
The galaxy Virgil appeared ordinary in visible and ultraviolet light. It was a young, calm object forming stars at a modest rate. Then James Webb observed it in the infrared. The galaxy transformed. At its center, a supermassive black hole, hidden behind a massive, dense dust cloud, was emitting enormous amounts of energy. The black hole was invisible in normal light due to the dust. Thick clouds absorbed ultraviolet and visible light and re-emitted the energy as infrared, exactly the wavelengths James Webb's instruments are designed to detect. This allows the telescope to see what others cannot, looking where no one else can. Virgil is not alone. James Webb has discovered several other galaxies harboring hidden supermassive black holes. These objects appear calm and ordinary in visible light, but infrared observations reveal intense activity at their centers. The black holes are feeding rapidly, consuming gas and dust, but the surrounding material blocks light at visible wavelengths. This discovery has significant implications for understanding the demographics of black holes. Previous surveys relying on visible and ultraviolet light may have missed a substantial fraction of actively accreting black holes. If many are hidden behind dust, the total number of actively growing supermassive black holes in the universe is greater than previously thought. These black holes are so dusty for a reason. They are still growing. Young galaxies contain far more gas and dust than older ones. The material feeding the black hole simultaneously hides it. As the black hole consumes matter, the surrounding accretion disk heats up and emits light, but this light collides with dust particles orbiting farther out before escaping. The dust absorbs the light and glows in infrared. Geometry also plays a role. If the dust disk around the black hole is viewed edge-on, it can block the center. We see the galaxy's stars and gas, but the black hole itself remains hidden. Without infrared observations, which can penetrate dust more easily than visible light, the black hole's presence would remain undetected. Virgil's black hole is described as overmassive. It is heavier than expected for a galaxy of this size. In most galaxies, the central black hole carries roughly 1/1000th of the total stellar mass. In Virgil, the ratio is much higher, indicating the black hole grew disproportionately fast compared to the surrounding galaxy.
This raises the question, which came first, the galaxy or the black hole? Traditional models assume galaxies form first and black holes grow inside them. Virgil suggests the opposite can sometimes happen. A black hole may form early, grow rapidly, and the galaxy builds around it over time. In that scenario, galaxies dominated by a central black hole like Virgil are less surprising. This discovery underscores the importance of multi-wavelength observations. Looking at an object in only one type of light gives an incomplete picture. Virgil looked very different in visible light versus infrared. To fully understand it, astronomers need data across the entire electromagnetic spectrum, from radio waves to gamma rays. James Webb's mid-infrared instrument was key in revealing Virgil's hidden black hole. Operating at 5 to 28 micrometers, it penetrates dust and detects the heat of embedded black holes that visible light telescopes cannot see. How many hidden black holes are out there? No one knows yet. James Webb has surveyed only a small portion of the sky. As observations continue, more galaxies like Virgil will be found. Each discovery improves our understanding of how black holes and galaxies co-evolve. The universe is full of secrets, most hidden behind curtains of dust.
James Webb is lifting these curtains one by one, revealing the structures and processes shaping cosmic evolution. Our understanding of galaxies is changing. The old picture, based solely on visible light, is incomplete. The new picture, enriched with infrared observations, is far stranger and more complex than imagined. James Webb identified a striking problem. Early galaxies are far brighter than predicted, not slightly brighter, but about 10 times more luminous than models suggested. This is not a minor discrepancy. It implies that the models describing galaxy formation and evolution in the first billion years after the Big Bang are missing something fundamental. Models include dark matter, gas dynamics, star formation, and feedback from supernovae and black holes. Cosmologists simulate cosmic history across billions of years on supercomputers, predicting how many galaxies should exist in different epochs and how bright they should be. Before James Webb, these predictions roughly matched observations. Hubble found early galaxies whose numbers and luminosities were consistent with expectations. Then James Webb looked deeper, and the picture changed. Far more numerous and brighter galaxies appeared everywhere, exceeding simulation predictions. Why are early galaxies so bright? One possible explanation is star formation efficiency. Perhaps the first galaxies converted gas into stars far more efficiently than modern galaxies. If every collapsing gas cloud formed stars without being disrupted by turbulence or feedback mechanisms, a galaxy would produce more stars in less time, and more stars mean more light. Another possibility concerns the types of stars being formed. If early galaxies produced a higher proportion of massive stars, they would be far brighter. Massive stars emit vastly more light than small ones. A star 100 times the mass of our Sun can be 1,000,000 times more luminous. If the stellar mass distribution in early galaxies was skewed toward heavy stars, total luminosity would increase dramatically. Supermassive stars might also contribute. These hypothetical objects would be hundreds or thousands of times more massive than typical stars and as luminous as entire galaxies. Even a small fraction of supermassive stars in early galaxies could explain the extreme brightness. However, supermassive stars remain theoretical. Black holes may also play a role. Active supermassive black holes emit enormous amounts of light while accreting matter. If early galaxies hosted more active black holes than expected, their combined emission could boost a galaxy's total brightness. Indeed, traces of black hole activity are seen in some of the brightest early galaxies.
The brightness problem also affects reionization estimates. This process describes how ultraviolet light from the first stars ionized the hydrogen gas in the universe. If early galaxies were brighter, they produced more ultraviolet light and may have completed reionization earlier than models predict. Observations of the cosmic microwave background indicate that reionization ended about 400 million years after the Big Bang. Brighter galaxies align more closely with this timeline. Dust enters the picture from another angle. Models assume little dust in early galaxies because dust forms from supernova remnants and takes time to accumulate. Yet some James Webb observations reveal dust in galaxies younger than 500 million years. If dust formed faster than expected, it could affect both luminosity and spectral distribution. Cosmological parameters themselves may be incorrect. Models rely on specific values for dark matter density, dark energy strength, and the initial density fluctuations seeded by the Big Bang. If any of these values are off, predictions fail. Adjusting parameters might bring models into better agreement with observations, but it would also affect other predictions. Some scientists argue that observations are being misinterpreted. Gravitational lensing or foreground contamination could artificially inflate measured brightness. Spectroscopy largely rules this out. The redshifts are real and the galaxies are genuinely distant.
The tension between models and observations remains one of the biggest surprises of James Webb's first years. Something occurred in the early universe that we have not fully accounted for, a process that made galaxies brighter, faster growing, and more numerous than expected. Until we understand it, the puzzle remains unresolved. Light traveling through expanding space changes. This is not a small effect. It is precisely why James Webb can see the early universe. Without expansion stretching light into infrared wavelengths, the most distant galaxies would remain forever invisible. When a galaxy emits light, its wavelength is determined by the atoms producing it. Hydrogen creates a bright line in deep ultraviolet